Okay, welcome back. So we're going to finish up these slides. We talked about pointers. They're just new boxes in memory, that's all they are, but they can have arrows coming out of them. They can store the addresses of other things. That's all. Okay? So this brings us to a magical concept called the heap, which is like the rest of these slides. Unfortunately, a difficult concept, so do pay a bit more attention here than you normally would, and also in your book when you're reading about it. Okay? So let's first remember what global variables did. Okay? So global variables are one way to make a variable live forever. You just define it outside of anything. Like here's main. Like you can define it outside, like above main, your variable. Okay? It'd be like int global equals 3 or something. And then because it lives outside, it lives for the life of the program. It lasts forever. Okay? It gets made. All global variables, actually, they are allocated, we say. They get made in memory right when the program begins. Okay? And every global variable lasts up until the program ends. The unfortunate thing about globals is the same thing that makes them so nice, is that they live forever. Maybe this wasn't an int. Maybe it was a vector that held a million things, and you only needed it for half of your program. Okay? You don't want to run out of memory in the second half of your program by wasting that thing. You don't need that space anymore. What if you had the ability to get rid of it? Yeah? That's the idea. So, we don't want to use globals all the time, okay? For giant things that don't need to live for the life of the program. We can make our own global memory. There's a way to make global memory for ourselves that lasts as long as we want it to last, okay? That's a beautiful thing. And we need to know about pointers because that is essentially how we get back new memory. We get a pointer to it. So now let me tell you exactly how your program looks inside of your computer's memory. Okay? So this is how it's arranged when you start your program. Okay? It's separated into these little, these different boxes inside of your memory. This is just one big memory box. Okay? It goes from small addresses to large addresses. Your program is split up into these sections. Okay? The text section is your program itself, the machine code instructions for your program. So your program itself is just a bunch of ones and zeros at the end of the day. Isn't that funny? So that's what the text is. You cannot write to the text section in most sane programming languages. Otherwise, you could change the program as it's running. No, we don't like that. Okay. There's also a separate spot in memory just for your global variables. Since they have to live forever, they need a spot made for them. That's unfortunate, right? So global data, that'll take up some space. Then you have the function call stack. So every time you make a call to your program, you have your call stack. Like here's main down here, who calls that, who calls that. And if you need to make another function call, you'll just add some more space up here. That's what it does. It makes its space as it needs to. So that's where all your local variables live, because they're all local to a function. They take up portion of this third chunk of memory. You see this? It has a dotted line. The stack is shared with something called the heap. The stack grows this way towards lower addresses, and this heap thing grows up towards the higher addresses. Interesting, though. What it does, the stack, it fights for space with the heap. Okay? This heap thing, though, that's the new thing. What it does is it holds dynamically allocated data. So globals, essentially, that you want to live for as long as you ask it to. Okay? You can take control over when memory lives and dies. It's very weird. So the stack and the heap, they share this chunk. The stack grows down and the heap grows up. Okay? So maybe I should have turned this diagram around to talk about it this way, but this is the way I like to think of it, even though this is kind of backwards. There is an issue, though, because these share the same spot in memory. They share the same little segment. If these ever, if you have too many heap variables and too many function calls, eventually these are going to clash one's going to go past the other. And that is what it means for your program to run out of memory, actually. You'll get a runtime error, and that's when your program ends, because the stack and the heap, these two things, they need to share data. They share the same spot in data, they share the same section in memory, and you don't ever want the heap to overwrite the stack, or the stack to overwrite the heap. Okay? So this has been a lot of words. Let me talk a little bit more about this new thing called the heap. Okay? So it is for creating and destroying memory, only when you ask it to. So like globals, yes, heap memory can potentially live forever, but unlike globals, you have control over when these variables get removed, okay? And one of the very, very nice things about the heap is that you don't have to decide up front, like before your program even happens, how many things you want to store in it. They can be like given to you from the user, like maybe the user gives you a number, like CN or something, and this n represents how many things the user is going to tell you. Like, okay, n could be 10, or it could be 10,000, yeah? That is the idea. And after that, then you can make space on this magical place called the heap for exactly that many things. You can make your, let's just call it an array for now. You can make your array of 10,000 things now that you know you need 10,000 things. And this can live on the heap, okay? That's the key. So this is how you do it. You use this operator called new, okay? It's weird. New takes a type, but you can think of it like a function. It takes a type, like you say new int, for example, and it gives you back a pointer to that type made on the heap, okay? This heap is a magical place that stores dynamically allocated things, so it makes you a brand new int if you ask it for an int, okay? It returns a pointer to an integer that was allocated on the heap, we say. So let me draw this. Let's pretend we have this line right here happening, okay? So we say new int. So here's the heap over here. When you say new int, the heap makes you, out of thin air, a brand new place, a brand new box that holds an integer. It's shiny and new. Yes? And then we're taking the address of this, maybe it's address 100, and storing it in an int pointer. That's how we can give it a real name. That will live on the stack because it's a local variable. N points to this place on the heap, we say. Here's n, it holds 100 and points here. Right now, the value holds who knows what. And then you can go and set that value on the heap, that shiny new int value, to 42. Okay? And then, just like a normal pointer, you can give it a value and use this integer for as long as you need to. It will live forever until you want it to die. So let me show you this. Call it heap.cpp. Oops. So here is a new integer on the heap. Okay? N points to a new integer on the heap. So n, it's some address, and we can set n to be some value. Star n, we can set that integer on the heap to be some value. So n and star n. So we have no control over this, but we just set the star n to be 42. So let me show you this. So this is apparently where this brand new fresh variable got made for us at this address, and we set it to be 42. And of course, this does change every time you run the program. So it really did change, but they were kind of close, it seems. Yay. So that's the idea. It holds 42. That's a brand new place on the heap. It lives for as long as we ask it to. Okay? We can pass it around places too. So we can get rid of it as well. Okay, so if we had, again, the same picture, actually let me just copy and paste it, that would be faster. We can keep the same picture, but we can also get rid of this memory right here whenever we want to. It lives for as long as we ask it to, but it doesn't have to live forever. You can say delete n, okay? Delete is a brand new keyword in C++. It takes a pointer to a heap location, okay? So n needs to be a pointer to some place on the heap, and then it'll go and delete the memory there, okay? So what you should do is always use delete once you're done with something that you have on the heap, and the heap will reclaim that memory. Isn't that nice? So once you say delete n, this is what happens. Oops. Maybe red would work here. This will go away. That's what delete does for you. Okay? So I can say down here now, delete n once I'm done with it. I'm done with the int that n is pointing to. So you just say delete n. Okay? I know this is a very contrived example because this could have just been a normal int variable. It's essentially lasting for the program anyway, but this is very, very useful stuff. Okay? So delete n, quite nice. Whee! Isn't that nice? Let me show you. Do I want to talk about it here or down here? Let's see. No, let me talk about it up here. Why not? Here is the reason the heap is so ridiculously cool. I can make a bunch of things. Int star. I don't know. I equals new int. And I can do cool stuff with I. And then you can be done with I. Delete I. Okay? This is the beauty of it. Oops. Sorry, I'm using ints already. Using I already. Let's change this to, I don't know, P. There. You can make a ton of things on the heap. As long as you clean up after yourself, there will always be enough room. That is the beauty of heap stuff. Isn't that nice? So this runs and it works. But if I didn't delete it, if I forget to delete, I will run out of memory eventually with enough things. And I'm scared to do it here because it might crash my virtual machine. But take my word for it. That's useful. Okay, so new and delete. Let's talk about arrays now, because how do we make arrays on the heap, you might ask? We'll get to that. So an array is secretly a pointer to the beginning of itself. What? This is something I didn't tell you. When you say int arr, this is a local array. It lives on the stack. But arr by itself is a pointer. It's secretly this. Like, we write it like this. Boop. Like, here's our array. But really, arr is a pointer to the first element. What? So let me show you that. Arrays.cbp, I guess. So int arr of size 42, cout arr. Oops. Oh, sorry, arrays.cbp. Excuse me. That's crazy. We thought we knew about arrays, but we didn't know everything. So arr, if you just say arr by itself without any brackets or anything, it is the address. It's the starting address of the array. So if I said like array 3 held 4, 5, 6, watch this, because this is extra weird. arr is a pointer to the start of the array. That is the first element of the array. If I dereference arr, what am I going to get? 4. Isn't that crazy? So yeah, that's what I wanted to show you. Arr is really a pointer now that you know about pointers. And yeah, that is very, very useful, because you can do what's called pointer arithmetic on arrays, and also C strings, because those are secretly char arrays, right? So this is why, finally, I guess I'm stealing my own thunder. We'll get to that in a few bullets. Okay. ARR1 is secretly translated into this. It's start at ARR, that's the starting location for ARR, and then add one integer of space and dereference it, okay? Which is weird to think about. If this is ARR, maybe it starts at address, I don't know, 4, then the next elements are at address 8 and 12 and 16. Secretly, ARR1, it goes here. You might think that this should be ARR plus 4, but C++ knows to go one integer size, not just one byte size. It goes by the type. So this is secretly what ARR bracket sum index is doing. It's secretly using pointer arithmetic, we say. So it's adding to the base address and dereferencing it. Dun dun dun. So here's how you get ARR1. You say ARR plus 1 dereference. And this should print 5. See that? It's the weirdest thing, but that's secretly what's happening. So ARR is the starting address, and 1 is the offset. Go one more int. So C++ knows go one more int, not just one more byte. It's cool like that. And you can do this for C strings as well, because those are just char arrays, right? They just have a special last element. And now, finally, it's been so many lectures since I told you I would explain it. Now you know why everyone uses char star instead of char array. Like, it's always char star argv bracket bracket, right? It's an array of C strings, which are secretly just char arrays. Why didn't they do like this or something? Well, this star is just a pointer. So a pointer to a char is equivalent to an array of chars. Sometimes. Okay? This is just as good as an array. Okay? That is all that you need to know. Dun dun dun. That is the beauty of it. So I can hold, this is the weirdest thing, int star p equals ARR. Yeah? See out p of 2. It's using p like an array. It's not an array, it's just a pointer. It's using it like an array, but it knows to translate it into this. And if it really was an array, which it is, it'll do the right thing. There's 6. I do encourage you to study this program. Even teaching it and knowing about it, it still blows my mind to think about it. It's a weird little concept. It really is. So with all of that, now that we know that arrays are just pointers to their starting elements, here's how you can make an array on the heap of as big of a size as you want. You can say int star p, like that's the starting address of the array. Please make me a new int array of size 42. That's how you do it. You say new int, and then you put your brackets. And so p now, p on the stack, it holds a pointer to the starting address, maybe it's 100, of an array on the heap of size 42. Yeah? And it's all shiny and new and nice. And this array can be as big as you want. You didn't have to specify it at the beginning of the program. You can get this 42 from a variable somewhere, a value that the user types. That's the beauty of the heap. It lets you grow or shrink your program's memory usage to whatever the requirements are for this particular run of your program. It's wonderful. So, yeah. Oh, sorry. P holds 100, not P lives at address 100. Got too excited, of course. Okay. Isn't that nice? And then, once you're done with this big long array, you can say delete to get rid of it. And then all of these 42 ints will go bye-bye, and they won't take up any memory, and maybe you can allocate a new heap array if you needed to. Int star AR2 equals new int of size 42. You can set these elements, AR2 of 0 equals 1, AR2 of 1 equals 2, etc. And use it like an array. AR0 plus AR2 of 0 plus AR2 of 1. Why not? And then once you're done with this array, you can say delete AR2. And deletion is the new thing. Okay? Hey, prints out 3. When you want to delete an array that you made on the heap, you have to tell C++ that this int pointer wasn't just a single int, like it was over here. No, this int pointer pointed to an array of things. You got to tell C++ that with these 2 extra brackets next to delete. That's all. So yeah, just remember these, and that's all. New and delete work for arrays now. Isn't that fun? Let's see here. Now I want to talk about another problem, because pointers problems happen, right? So let me show you a memory leak. Okay, so this is what happens when you lose access to data in your program, and you can never find that data again, even though it's taking up space. It's unfortunate. So here's my example. You say int star I equals new int. So here's the stack in the heap again. So you say int star I equals new int, so that makes a brand new shiny int on the heap, and I is the local variable that's pointing to it. And then you can set that value there to 42, and then you can reset I to be a brand new integer on the heap. So this gives back an address of that thing, and you're putting it in I. And this is where the problem starts, because this is a brand new box. Maybe this was address 100, and this held 100. This is address 104 maybe. And so now you're doing this. I now points. Now I now holds 104, and the heap variable that it's pointing to is over here now. And we can set it to be not 42, but 43 with this line. And look what just happened. This int right here, these are both brand new ints, so shiny and new, but you gave up the first one, and it is very sad. Okay? You cannot get rid of this one. We just leaked memory. We can't access it, we can't get to it because we deleted it. You see that? Oh, sorry, we didn't delete it. We deleted the pointer to it. We lost any way of getting to this location. That's what a memory leak is. And if you do this enough in your program, you'll run out of memory. Okay? So that is that. And let's see here. I do want to do an example in a second. Do I want to get to that after? Yeah, but let's do it before this next one. So, okay, before the meme, let me show you an example of using the heap to actually do some cool stuff. Let's make a program where the user gives us a number, and we will make an array of that particular size on the heap. Okay, and then we can use that to fill up the array. Okay? Ask the user for number n. We'll then ask the user for n things, and we'll put them in the array. And then we'll also get the sum of them, or something like that. Then let's print the sum of that array, and then finally remember to delete the array. So that's what I want to do here. Okay, that'll be my example. So let's go and do it. Okay, so let's say, I don't know, heap example.cpp. Why not? Let's get a number from the user. And then we'll use that number to make a brand new array on the heap. Just like this. And we're going to have it of a certain size. Actually, let's just make a function that does this to show you that it doesn't all have to be in the same function. Int star get array of size, or maybe like make heap array of size. So this will return a new int of size. Isn't that fun? And so this is telling you, it's making it very clear that heap things go between function calls. This is going to return back the starting address of this heap array. Okay? So, I don't know, int star arr equals make heap array of size n, and then we'll ask the user for those n things. We'll ask them and we'll get it. Okay, so int next num, cn next num, and I guess after we've done that, we will sum all the elements, which involves another loop. Sum. Again, this is a contrived example, but it's a cooler contrived example. ARR at I, because you can use the array syntax with this. It's totally fine. Cout sum. And then we're done with the array. Delete ARR. But remember to use the brackets, because it was an array that was made on the heap, not just a single int. Okay, so here is this silly function / program. And let's say 4 things. And it'll go and make an array of size 4. It'll give back a new integer on the heap of that size. And then it'll ask us for those things, and it will sum them together. And apparently I did something wrong here. Let's see here. ARR of I, sum plus equals ARR of I. Oh, I never actually put the number in to the array. That'll do it. There it goes. And this changes, like it'll make an array of size 5 now. Isn't that beautiful? Now the sum is 15. It's lovely. And then it deletes the array as if nothing ever happened. So that is my silly little example of heap stuff. And I added an extra function just to prove to you that it's kind of like globals. Whatever you do here is, whatever you do with new exists for the life of your program until you stop anything, until you say delete. Okay? You can say delete in a different function to which you said new. There we go. Okay. So yeah, that was my little example. And now I want to break it to you that vectors and strings secretly have been using arrays that have been allocated on the heap this whole time. You've been using the heap all this time. Okay? So enjoy this custom meme for this class. All right. So 2 more sections in these slides, and then we're out of here. This first one, called linked lists, is something that is a huge concept in CSCI 41, which means that I'm not going to hit it very hard in this class, but you will have maybe a Xylab about it, and that'll be all. Okay? I'm not going to test you about it or ask you in a virtual machine lab to do anything, but I think it's a really good example. So that's why I'm showing it to you now too. So it answers the question, like, when will I ever want to use a pointer instead of a reference? Like, what good is a pointer then if I could just use references most of the time anyway? And also, what's a good reason to use the heap? You're also forced to use the heap when you want to use, you're forced to use pointers when you want to use the heap. So, I mean, what's a good reason to want to use the heap? Because I've been giving you contrived examples again. So let me show you the magic of linked lists, okay? Which you will learn more about if you take CSCI 41. So a linked list is what's called a data structure. It's a way of structuring data, making it all nice and orderly. And a linked list is a bunch of nodes, okay? And each node holds a piece of data, so maybe a number, and then it holds a pointer to the next node in the list. It's very, very nodey. So let me show you this. Instead of like the array, 1, 2, 3, where everybody's right next to each other in memory, you can make a linked list called like L, let's say, which is a pointer to a bunch of nodes, okay? And these nodes are usually made over here on the heap, where they look kind of like this. They hold the data part and the next part. So maybe it holds 5, and then it holds a pointer to the next node, which again looks like this. Okay, which is, it's secretly a class, so it's more like this. This is the data, this is the next. And I'm gonna draw it like a little 2-element array, because it's easier that way. 5, 6 points to the next node in the list, 7. Okay, so this is how you can hold 3 numbers in an array. This is how you can hold 3 numbers in a linked list. And just like C strings, you know that you're at the end of a linked list when you have a null next pointer, when you have a 0. So that's like your null terminator character. It's very interesting. So these are actually a competitor to arrays/vectors. It's easier to do some things with these linked lists as opposed to arrays. In particular, putting a value in the middle of an array is the world's hardest thing to do. But for heaps, or sorry, not for heaps, but for linked lists, it's super easy. You just make a new node and move 2 pointers around. That's all. Okay? Or maybe that's the one we wanted to do. That is all. So they do have their trade-offs, and I want to show you how to make this in code very, very, very quickly. Okay? So let's model this in code, and yeah, that's essentially all. This will give you a good head start on your Scilab. I think I'm going to give you one about linked lists, and you'll read about it in the book too. Linked lists.cpp. So every linked list is made up of nodes. Okay, so this one is the first node holds 5, the second node holds 6, the third node holds 7. Node star 5, I guess. New node. Do that for 6 and for 7. So I'm making 3 nodes on the heap, yes? And I can set their data and next values. And I guess I'm going to have to do this down here because 6 doesn't exist yet. Oops. Darn. There we go. Yeah. 5, 6, 7, 7, null pointer. Okay, so here's how you do this. You make 3 nodes, and you set their data and next pointers like this. So 5, its data holds 5, of course. 6 holds 6, 7 holds 7. And 5 points to its next thing is 6. 6's next thing is 7. Okay, easy enough. And this is how you define nodes. They hold, well, the data, which can be an int in this case, and then also a next pointer. What's it a pointer to? What is everything pointing to? This next is a pointer to another node. What? It's pointing to itself. It's pointing to the same type. We've never seen this before. So you can say node star here. Okay? That is quite odd, I think. with your current level, but it is something that people like to do. So the next thing in a list is a pointer to another node, the same type that we're defining. It's got itself inside of itself, and null pointer is how we stop it. Okay, it's how it tells that how we tell it that it's done. So this is how you make the list. And let me show you this. Let me show you how to add a new node to the beginning. Vectors are really bad at this. Okay, so this is one place where using a list might really help. So finally, I guessed, let's say node star L, that equals 5. Okay, this is like the first part of the list. So if we have our L, and we have our list over here on the heap, we have our 5, and our 6, and our 7, and our null pointer, we can add a brand new node to the beginning. Maybe we can add 4 by saying new node and setting its next pointer and setting L's pointer to point here instead. Okay? So this is all you have to do. Make a new node. Might as well use colors because it's fun. Make a new node. And then just move around some pointers. 4's next is 5. 5's next remains whatever it was. Okay? This is how you add a new node to the list, and it goes along that way. Isn't that weird? So let's add 4 to the beginning of the list. We can say node star, I guess we can do it here, node star 4 equals new node, and we can do 4's data equals 4, 4's next equals the node 5, okay? Because this is what 5 points to. Pointing to this node, we set 4's next to be the address where this node begins, and that is exactly what 5 holds. It holds the address of that node. I know these are weird little terms, but I'm not going to test you on this. You'll just have one little Zilab about it, okay? So this is to get you started, to make the book make a lot more sense, I think. Okay, so now we can just set L to be 4 instead of 5, because 4 is the new start of the list. And now we can go through it. Okay, here's how you can go through a list. You can say cout L arrow data. That'll give us the 4, because L points to 4. Let me show you that. And then, if you wanted the 5, here's what you could do. You could say L, well, it's L arrow, that's here. Next arrow, that's here. Data. Cool, huh? That'll get the second node's data. And that should print the 5. What? And then you can play this game for the other two. It's, well, whatever comes after 5. Next, next. Data. Next, next, next. Data. Yeah? Four, 5, 6, 7. So L, that's L. L's next, that one. L's next, that one, get its data. L's next, data. Yeah, that's essentially how I want you to think about it. You'll learn a whole lot more in CSCI 41, and the book will be a bit more thorough as well, if you're interested. So that is linked lists in a nutshell. This is not something I'm going to test you on, so don't worry about it. You will have to do one little thing in the book, though, I think. Okay. Now, I want to show you, because I've told you about all the horrible things that go wrong with pointers, let me show you one way to make it better, okay? To, like, understand your problems. Because you're going to have a ton of Sig faults. I'm sorry. It's just a way of life. GDB, this thing that I'm about to teach you, will help you make it right. Okay, it'll help you find where your errors are. So GDB, it stands for the GNU debugger, and GNU are the people who made G++, and G++ is the GNU C++ compiler. And so GDB kind of comes with it. Okay, it's the debugger. It makes things very, very nice. It's a program that runs your program, and it gives you information about it as it runs. Okay, it can tell you, like, at this line the value of the variable x is this, and if we're in a loop, you can print out every value that x changes to if you wanted to. It tells you the line number where the runtime error happens if you run it inside of GDB, your program. The only thing that you have to remember to make GDB work is to compile with the -G. -G for GDB, right? So what this does, this -G, is it adds debugging information to your compiled program. It like bakes in the line numbers, which is really nice. Bakes in the names of the variables. That's essentially what it's doing. So if you want to compile foo.cpp, you say, well, as usual, G++ standard equals C++ 17, but you also say -G, okay? And then you can say -o-foo. That's the key, right there. You got to add that too. Okay? So I'm going to show you a very simple example. We're going to fix a Sig fault with GDB. Okay? So let me show you that. Here we go. So I'm going to make Sig fault.cpp, and we're going to fix it. Dun, dun, dun. Or at least going to discover the error. Okay? So maybe I should say it like this. Discovering / understanding a Sig fault with GDB. Okay, so here's how we're going to compile. We're going to say -G. So that's the first thing. You notice what's going to happen, right? If we run it, we're going to get a Sig fault. Let me just run it normally to prove it to you. Unfortunately. So we got a Sig fault. Seg V, they say. Okay, let's go back to this. Let's compile with -G in addition, okay? So we say -G, you can put it wherever you want before the name of the program. You can put it before or after the standard part. I'm going to put it there. Nothing changes, it still compiles, but it compiled with those extra debugging header helpful things, okay? And so now instead of running /sig fault, we're going to put GDB out in front. We're going to make GDB run the program for us. Okay? So instead of this, I'm going to say GDB. Yeah? Hit enter, and this plops us into GDB. It gives us a new prompt, and here's how you use it. So the first thing you do is say R to run the program. R, enter. And now, here's the beauty of GDB. It found that, yeah, we got a seg fault, segmentation fault, cool. Here's where it happened. I think you can see how cool this is now. It's like, okay, it happened in main, it happened in segfault.cpp, colon, the colon means the line number. It happened on line 6. That's amazing. It's like, okay, this line, and it prints it out for you because it's nice. Like, okay, this line, something happened with this line. That's what caused the error. And I think you can see if you're a programmer, like, okay, cout is written by the G++ people. I don't think there's a problem in cout. I don't think there's a problem in endl. I'm pretty sure it's a problem with star p. So maybe I should look into what star p is. And now, that's the beauty of it. You can say BT or backtrace to view your stack, like where you came from, because maybe you called a bunch of functions. But right now there's only main. We've only called main so far, but it shows you where you are in each function if you use BT. And what else? You can print the values of variables. Oh, goodness, is this wonderful. So you can say print x, where x is a variable, and it will tell you its value. So here's p. I'm going to print p. Oh, at this point in the program, on line 6, when this is executing, it looks like p is 0. Oh wait, I'm trying to dereference it. I see why there's a seg fault now. Do you see that? This is the greatest tool in your arsenal. GDB. It actually would have helped you when you were learning vectors, I think. We didn't have time to talk about it then, but now we do. Okay, this is how you use it. You can say print whatever variable you have in your program. It's like, okay, dun dun dun. Let's add a variable x. Let me just get out of this. You can get out of GDB by saying quit. Quit. You say Y for yes, we want to stop the program. And then you can recompile, rerun in GDB, R for run. It's like, okay, yeah, we got a Sig Fault. You can print P again. You can also print any other variable, like X. That one wasn't the problem, but it remembers its value. It's the greatest thing. And then quit. Yes, I want to end the program. Thank you. That is GDB, and I hope you can see how useful it is. It tells you what line the error happened on, what line the runtime error happened on. So the next time you get a runtime error, compile with -G and just plop into GDB and see what's going on. It'll tell you the line number where it went wrong, and you can print out the variable values. Okay, I don't think I need to convince you anymore about how great GDB is. Now let me give you one exercise which is really multiple, right? I think a really good idea would be to change an old lab or old Zilab or old in-class example, one that didn't, that was before we talked about pointers, and use pointers instead. Like, add some levels of indirection to make sure you're understanding how to like maneuver around with all the stars. Okay, use the heap so that you understand how to make new things, how to delete them, how to pass the pointer around so that you don't leak anything. Okay, that is wonderful. Or change all the function parameters to take pointers rather than references or just values. That would do it. Okay, I think that would be a great idea, and that's where I'll leave you. So I'm pretty sure you get the joke now. You're welcome. I'm sorry you had to learn about the train wreck that is pointers in the heap, but this is making you grow as a programmer, I promise. Okay? So do come to office hours, do yell at me if anything at all is not making sense. This is a very difficult concept. I'm very aware of it. Okay? It took me forever to get this ingrained in my mind, and so I can only imagine how hard it is for all of you right now. Okay? So I am here to lend an ear and a hand. So do yell at me if you have any questions. Otherwise, I will see you later.